can we improve this method. So a quick introduction to the models of hydrodynamic dispersion that consider species-specific properties. Essentially, this is the classical model that we are all used to it. It's the transfer dispersion model where dispersivity is a proportionality factor of the velocity. And so experimental analysis have shown that expression of this form where there is an exponent beta that adds some nonlinearity to incomplete mixing to mechanical dispersion, then these expressions fit better the experimental data that these articles have gathered, let's say. And also there is a specific or explicit, let's say, dependence on molecular diffusion for the mechanical dispersion term. So this is quite interesting and mostly different to what we are used to. And so this model is based in some early formulations from Baer and Bachmann, some really old articles where, in fact, mechanical dispersion contains an additional function that modulates the magnitude of dispersion. And so just to give an example, these authors, they work mostly analyzing fluorescein and oxygen. And although the diffusion coefficient looks really small because they are usually expressed in international system units, when you transform this to more, let's say, experiment scale units, then you can see that the differences are more notorious. And some typical parameters for these models, the exponent beta is usually around 0.5, and there is this parameter delta, which is a medium property that usually oscillates between 5 and 6 for rounded microspheres. And so what I want to remark in this figure here from the article of Hochstetler 2013 is that dispersion, it is different for a wide range of velocities. So even in advection-dominated conditions, dispersion remains different for these substances. Okay, so let's say that you have a transport model already implemented with the linear form, the classical dispersion tensor, and you want to play more or less with this nonlinear model, then you can test these formulations by redefining dispersivities. Essentially, you can pre-compute the value of dispersivities given a flow velocity. You compute the Pecklet number, you adopt a characteristics grain size, this parameter delta, this beta exponent, you can take it like 0.5 for transverse dispersion, close to 1 for longitudinal dispersion. And so if you pre-compute dispersivities with an expression like this, then it is possible to integrate this nonlinear model into a classical transport code. And so, for example, I did some really simple examples using the transport module of the current version of ModFlow. And without any modification to the source code, let's say, I compute the value of dispersivities, I specify this to the model, and then the model automatically captures the effect of compound-specific properties in the solution that it provides. And here I'm comparing these numerical results against analytical solution for the two-dimensional homogeneous problem. So in this case, it's quite simple to pre-compute the value of dispersivities. Velocity can be obtained analytically by means of Darcy's law, but let's say that you have an heterogeneous problem, so that requires some fine-tuning. Let's say in the case of a heterogeneous problem, you would need to solve the problem in a steady state, then adopt those velocities for computing a distributed Pecklet number, and then specify these dispersivities to the model, and it should work exactly the same. So this I leave for you if you are doing some transport models and you are using some code. If you compute the value of dispersivity with an expression like this, you can get the benefits of transfer species-specific dispersion. So in terms of reactive transport, usually, or one of the methods that has been widely studied within our research group is that the method based on components, where the transport equations are reduced by introducing a chemical component, which essentially is a linear combination of species, where the linear combination is performed by means of a component matrix. This matrix is a function of the stoichiometry. So what I want to say with this is that essentially, whether or not we are considering species-specific properties, the component matrix remains the same. So it's a function of stoichiometry. The process of getting to the transport equation for components should be exactly the same if we are in the case or not where transport properties are different. And so the usual form of this transport equation is the one I'm showing you here in equation 9. You have a single dispersion tensor for the components. And so my question is, what happens when we consider different dispersion? And this is a problem that has been around, let's say, open without addressing for quite a while already. So I want to give an overview or to more or less explain the idea of how to derive the form of species-specific dispersion and components. So I just want to remember that the multi-species reactive transport problem is a problem involving two vector spaces, and that might lead to some confusion sometimes, but I hope I can make it more clear for you now. The one space that is the space that we all know is this spatial coordinate space. It's the three-dimensional domain where the operations that participate in this space are the dispersion and the gradients, spatial gradients of species. Whereas we also have the space of chemical substances. This is a completely different vector space, and is the set of operations that participate in this domain are the operations involving the component matrix, the stoichiometry, and the vector of concentrations. And so what I mean when I write the temporal derivative of the vector of concentrations, what it is implicit here is that we have essentially the derivatives of all of the species. It's a vector of transport equations in the end, okay? And so it might be confusing because you have also this vector quantity, which is the dispersion tensor. So you have like two vector spaces playing, and that might sometimes break your head. And so what one can do to address this problem from a more, let's say, generalized way is that we can define a block matrix of hydrodynamic dispersion. This is a matrix that is a block matrix. It means that each of these entries is a submatrix, let's say, but the linear algebra is the same whether or not is a block or a normal matrix. And so in this case, this matrix operates over the vector of gradients of concentrations. And if you multiply, this is a diagonal matrix specifically. If you multiply this matrix by the vector of concentration gradients, essentially what you get is the vector of dispersive fluxes. Is the linear algebra is exactly the same. The only difference or conceptual trick, let's say, is that this matrix is defined as a block matrix. And so one can rewrite the set of transport equation instead of this matrix and then apply the components as usual, all right? So here there is nothing different to the usual derivation of this problem. However, the components now transport equation, the difference with the normal transport equation for component is that now this equation is also nonlinear. So we have, because we are considering different transport properties, now we arrive to, let's say, the second nonlinearity that appears in this problem. And this case, the nonlinearity is given because we have this sort of equivalent dispersion for the components, which is a function of the component itself. So you could imagine this hydrodynamic dispersion for the component is a function of U. So we have the transport equation for U like a dispersion coefficient, but is a function of U also. So that is, it complicates the problem, but is something that we can solve. So in a binary system, which is the problem that we usually discuss for this kind of problems, we have analytical solutions for the concentrations in terms of the components. And so this is, you can consult the articles of the Simoni, for example. This is a well-known analytical solution for the secondary species when you have simple binary reactions. And so if I would like to compute, let's say, this equivalent component for this kind of problem, it is possible to do it because I know the expression for the concentration. I can compute the derivatives of this concentration, which, by the way, a small detail, this matrix J here is a matrix of derivatives. This is like a Jacobian of the concentrations in terms of U. So this is a matrix of derivatives of C in terms of U. And so I can, given this equation for C, I can compute the derivatives, I can compute the equivalent dispersion, and then what I see is that this dispersion is a function of the component itself. So something to just verify that everything is more or less okay. If I consider that the dispersion for the primary and the secondary species is the same, then this term is zero. So the dependence of the component disappears, and this term over here transforms to the normal dispersion. So essentially, you recover the same dispersion for all the species formulation of components. There are also some additional developments in this regard. You can compute the reaction rates and so on, but I'm not going to get into more details into this seminar in this regard. And so the last set of nonlinearities that appear in this problem, they are enclosed in the idea of ionic interactions. Usually in reactive transport, we are dealing with ions uh, for their chemical reactions. And so when we transport ions, there is an additional transport process for the usual dispersive flux, let's say. And this additional transport process is known as the migratory flux. Is a term that is dependent of the electrostatic gradient potential. And so this term over here, let's say you could understand this term appears because when we have charged substances, there are some restrictions for the transport of charged substances. These restrictions are called the restriction of electroneutrality, and also no electrical current in the absence of electric field. So essentially, this gradient would appear if we have a positively charged substance, let's say, traveling in a cloud of negatively charged species. This gradient that will form a electrostatic gradient that will add an additional flux. And so essentially, this process, what it tries to do is to balance or preserve neutral the charge of the whole system, of the whole solution. This is true as long as there are not external electrical fields applied to your system. And in this, for this topic, if you want to dive a bit deeper, I would recommend the articles of Podroa, 2004, also Munir-Usama et al. In 2014, Munir-Usama and Rolle in 2015. There are several articles addressing this topic, both experimentally and numerically, that essentially show that the existence, and they prove it, of this migratory flux when we are working with ionic substances. And so this, by means of the principle of electroneutrality, the kind of nonlinearity that appears here for me is the ugliest, the most maybe difficult to understand, is that now the transport equation for these ionic substances is not only dependent on the concentration gradients of the substance itself, it's also dependent on the concentration gradient of all of the other substances. This is only because these substances possess different diffusion or different dispersion coefficients. And so now the transport equation is way more complicated because we are also adding over the dispersive fluxes of all of the ionic substances we have in our system. And so in this case, dispersion, there is also an equivalent dispersion coefficient. This coefficient is slightly different because it contains the normal dispersion coefficient of the substance plus this correction term that depends on the charge of each substance, the concentration of the substance itself, and the concentration of all of the other substances. So this is highly nonlinear, and as you can imagine, really hard for me at least to understand and to solve. And so if you believe I'm lying to you, I just want to say that that is not the case. This multi-component diffusion is something that in your favorite geochemical code exists already in FreakC. You can find this functionality in the transport module if you want to play with it, let's say. You have to play with the multi-D option where you specify diffusion coefficients for all of the species. And essentially the diffusive flux in this case is computed as usual, plus a term that corrects for the charge imbalances, let's say. This CV term here is the charge balance correction term. So as a summary, the experimental evidence shows us that mechanical dispersion depends on species-specific properties, specifically on molecular diffusion. This occurs even in advection-dominated scenarios, which is let's say, one of the most common arguments to say that dispersion is the same for all substances. That is not necessarily the case. That is what I want to remark. And so in this regard, nonlinear expressions depending on the flow velocities have shown really good agreement with experimental data. The model is a bit more complex to have these additional parameters moving around, but the articles and experiences mounting and providing data for these parameters is growing. So you can more or less play, if you're curious, with these models really easily. So this, the fact that we have different mechanical dispersion now for substances leads to some challenges into the method of chemical components. The components are well defined as usual because they are only dependent on the stoichiometry of your reactions. There is no limitation that say if your diffusion or dispersion coefficients are different, you cannot define the component. No, the component is well defined, exists as usual. But the problem is now that the transport equation for the components is non-linear and it depends on the component. So let's say in each time step, we have to grab the values of components, then compute dispersion in terms of this value and continue to the next time step if you want to see it from a numerical perspective. And just to complicate our life a bit more, we have in the end this a quick overview of what ionic interactions are. This is a process that appears when we are working with ionic substances. This flux, essentially what it tries to do is compensate the dispersive flux in order to comply with the condition of electroneutrality or no electrical current in the absence of external electrical fields. And so essentially in the end, this formulation of ionic interaction, what it says, it provides us with the most complicated nonlinearity, in my opinion, which is essentially that the transport of one substance is now depending on the concentration gradient of all substances. I would say by looking at the fluxes of this last form that when we have really low concentrations of these ionic substances, we might at least try to suppose that the migratory or the electrostatic gradient contribution is not as important as dispersion. That I could more or less accept, although it should be accompanied with more strict analysis, I would say. So to close, some references, and thank you.
No, está desconectado. La cámara. Sí, pero no, bueno. And you cannot see us, I think.
I cannot see you.
I see the full screen because the candidate recording you ask you want to open your camera, but someone recording. You can see the full screen. Exit. There. Is there? The book. Someone ask.
No. Hay un problema. There's a problem. You cannot see us, sorry.
I can hear you though. I can hear you.
So okay. Any questions?
I have some.
Okay.
You turn on the slide. Slide.
Okay. Can you put the slide so?
Yes, there it is. Which one?
14, I think. The equation 14.
Which one?
Equation 14. I don't know which page. Equation 14.
Yes.
What does the JU mean? The JUI?
Yes.
Which kind of Jacobian? Jacobian or what? How?
This is the Jacobian of concentrations in terms of components. So this is, if you can see it like derivatives, is the C at the U and in all of the in all of the elements of this space. Let's say this is a change of variable. You can see like the gradient of C. You can see it as a change of variable. This step from gradient of C to the gradient of U multiplied by the Jacobian. This is a change of variable typical of calculus multidimensional domains.
Yes. Another slide. Next, I think the next about the electricity charge. The slide, the page with electricity in the charge.
This one?
One with the charge, electricity charge.
This?
The next with the two figures. I think the next. Yes, this also has a J. I see that. The J.
Yeah, so the J, you mean in equation 19 and equation 18, this J is the diffuse dispersive flux, let's say. It's dispersive flux. So the condition in equation 19, what it's saying is that if you multiply the charge by the flux, there is no current, no electrical current due to the transport of this species.
And you said the flow, the velocity, you said the velocity is very important for the dispersion. But I think I didn't, maybe I missed something. I did not see any flow in your equation, I guess. You said in your summary part, you said it's very important. Even in the convection control case, the dispersion is important. But in your equation, there's no convection, I guess. I'm not sure.
So I will explain. This in this case, this J is only dispersive flux. All right. The term of velocity is hidden in this case in these derivatives. These derivatives are material derivatives. So if you expand this material derivative, you have the partial derivative plus the divergence of velocity times porosity times concentration. So the velocity is implicit in this. Let's say the advection term, usual advection term from the transport equation, is hidden in this material derivative.
I understand. Thank you.
Okay.
Okay, more? Let me just do one question about, because you put a lot of diffusion, dispersion, equations or laws for calculating the diffusion coefficient or the dispersion coefficient. Are these very empirical, let's say, or is there some? Because I think the one you showed me from 3C, I think has some theory behind.
Yes.
With the other one.
Yeah. So let's, if I understand correctly, Martin, you mean this expression for dispersion, right?
Yeah.
So this expression, well, the first term is pore diffusion. This is molecular diffusion corrected by tortuosity. And then you have this term here that characterizes mechanical dispersion. And yes, this parameter beta, it is empirical. This delta, it is empirical. But this model is based, let's say, or derived from an early version of dispersion that comes from Beer and Bachmann, let's say, where this the full form of dispersion contains the dispersivity times the velocity times this function here. This function has a meaning. It tries to represent the effect or how an elementary mass is changing is changing in time due to dispersion. And so the exact form for this function is not well known. Beer and Bachmann, they propose one which is similar to what you see inside these parentheses in this equation 4, but the later versions of this function are more or less different. It's similar, not exactly the same, different. And in fact, they propose a function that essentially when the Peclet go to infinity, this function goes to 1. But what these authors say, in fact, from their experimental observations, if they do that, which is the broken line in this plot, in the left plot, let's say, if they do that, then dispersion follows this line, and that is not what they observe from the experimental measurements of dispersion. And so they propose, based on this original formulation from Bear and Bachman, they propose a modified empirical form of nonlinear dispersion, which is the one you're seeing in equation 4.
And what about, because actually in our group we do a lot about mixing and spreading and rate mass transfer, and I don't know how many methods to do this mixing, spreading better. How do they relate with this these kinds of ways of formulating the dispersion?
Okay.
This is already a little bit old, I think.
Sorry?
This particular.
Yeah, so the original is old, is 67, sure, but this one is new. This one has been addressed since 2010. In fact, this is the first appearance of this expression, and so this expression, yeah, this exponent beta, this beta exponent that you see here, this is an exponent that intends to characterize the incomplete mixing inside a pore channel. And so there are articles in that sense. I would recommend Rolle 2012. And in this article, they analyze the effect of incomplete mixing inside a pore channel, and there are some pretty nice figures that essentially explain why this beta makes sense. Yeah, but what I think is important to capture here is that based on experiments, these guys, they say, you know what, the usual classical dispersion model where dispersivity is constant for every substance is not providing good results for the experimental measurements. So they say, okay, let's go back to the basics, let's say, to this really old expression of dispersion. This function f, as I said, it could be a bit obscure because it's a function that models how a single mass is deformed due to dispersion. So it's hard to say, and it's harder to understand and probably to define. So in fact, what they do is, all right, I will take the form of this function really old, and I will accept or assume that this function could be nonlinear. Yeah, and so this nonlinear expression, I don't want to I'm not selling this. This is what I'm seeing. This nonlinear expression appears in the articles of these guys that I'm showing in this slide, but also in all of the articles analyzing ionic interactions from Muniru-Zaman, which I also mentioned, some reactive transport applications for iron precipitation. This expression has been, I mean, it's widely used, and so it seems that it provides a better picture of mechanical dispersion for high velocities.
Okay, thank you. I don't know, some other questions also from the online audience. I think there are no other questions from audience. So I think we can end the seminar. Thank you very much.
Thank you to you all.